بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. Donc, we would like today to for defense of PhD studies of the student Huam Sabrima under supervision of Professor Afoun Abd Mohammed and co-supervised by Professor Shlermi Mohammed Lemine. Firstly, I would like to warmly thank Professor Hamlawi Youssef from University of Soghras for his acceptance to be member of this jury and to come here to Gelmar to give his experience and his feedback. Also, I would like to thanks Professor Nigri Soria to accept to be member of this team for this defense. The title of this PhD studies is theoretical and experimental study of the electrochemical detection of chemical compounds in aqueous medium. Mrs. Huam Sabrina, you have about 30 to 40 minutes to explain the big idea or the big finding of your thesis. Take your time and try to explain for us and for the audience your work, and don't forget this today is just to explain for us your ideas and your PhD students and your thesis for PhD diploma. Thank you.
So, good afternoon everyone, respected jury members, family and audience. I extend my sincerely thanks for your presence here today. It's an honor to present before you as I define my doctoral dissertation. So today I'm going to be talking about my work in the title of Theoretical and Experimental Study of the Electrochemical Detection of Chemical Compounds in Aqueous Medium, under the direction of supervisor Professor Afoun Abd Mohammed and the co-supervisor Professor Shlermi Mohammed Lemine. In this presentation, I will start by giving a brief introduction to research area, highlighting the necessity of using electrochemical techniques with simulation. Following this, I will define the problem statement and research objectives, and subsequently, I will provide an overview of some theoretical background relevant to this study. Then, I will describe briefly the experimental and simulation methods that use in the thesis. And then I will explain how to simulate linear sweep bathymetry for soluble-soluble systems. Next, I will present and discuss our research results involving theoretical results and theory experiment validation. Finally, I will close by conclusions and perspective works. Let's get started talking about research area. Electrochemistry is an interfacial science between chemistry and electricity, playing a pivotal role in both everyday life and advanced scientific and technological applications. This field encompasses of diverse array of devices such as electrochemical sensor, electrochemical battery, as well as phenomena including corrosion of iron and electrochemical synthesis. On microscope level, electrochemistry is the study of electrochemical reactions, which aims across an interface between an electrode and electrolyte. These reactions are classified based on the nature of redox couples involved three major types, such as soluble-insoluble, soluble-soluble, and insoluble-soluble. And depending on the electron transfer charge, the electrochemical reaction are on three behaviors, such as reversible, quasi-reversible, and irreversible. Furthermore, these electrochemical reactions are fundamentally governed by thermodynamic and kinetic principles. This is why it is becoming increasingly important to understand and control the electrochemical reaction. For this purpose, electrochemical bathymetric technique stands out as one of the main sophisticated electroanalyticals, involving linear sweep bathymetry and cyclobathymetry, which provides and more insights into about mechanisms and kinetic and thermodynamic information of electrochemical reaction. On the other hand, in voltammetric experiments, computer simulation becomes an attractive and successful approach for analyzing electrochemical systems, engaging a more qualitative and quantitative interpretation of the experimental voltammetric data. For this reason, voltammetric simulation is always in demand. Our research focuses on simulation of the linear sweep voltammetric responses for soluble-soluble electrochemical systems under quasi-reversible conditions. Moving now to define the problem statement and the research objectives. The main characteristic features of linear sweep voltammograms that used for diagnosis of electrochemical reaction are the peak current, the half peak width, and the peak potential. By full analyzing of these voltammetric peaks, kinetic expression have been deduced in both reversible system and irreversible system, describing the peak current and half peak width and peak potential. And to quantify the reversibility and kinetic of electron transfer reaction, the electrochemical rate constant is an important parameter, and various diagnostic criteria have been developed based on this analysis of the voltammetric peaks for the determination of standard rate constant in quasi-reversible system. In this direction, for the determination of standard rate constant for quasi-reversible kinetic for linear sweep voltammetric characteristics, we noted the following. For soluble-soluble, Matsuda et al. Have established the three kinetics diagrams relating to the voltammetric peaks, which provide a rough estimation of standard rate constant, and they remain insufficient for qualitative analysis for soluble-soluble system. While for soluble-insoluble system, Abik et al. Have presented the same kinetics diagrams as Matsuda and added a series of equations which provide an easy and direct estimation of standard rate constant. To our knowledge, there is no practical equations that allow a direct determination of standard rate constant for soluble-soluble systems via the use of linear sweep voltammetry. Our research objectives were calculation of theoretical linear sweep voltammetry responses for quasi-reversible soluble-soluble redox reactions via semi-analytical simulation. Development of practical equations from linear sweep voltammetry to use in direct determination of standard rate constant for soluble-soluble systems, whatever the degree of reversibility. And validation of the applicability of the developed equations with experimental tests, including electrochemical oxidation of ferrocyanide, electrochemical detection of dopamine, uric acid, and ascorbic acid. Now we go over to present some theoretical background relevant to this study. So, here I am going to cover some fundamental laws governing an electrochemical reaction in both equilibrium and non-equilibrium conditions. Starting with electrochemical equilibrium, we have the next equation. This equation quantifies the relationship between the electrode potential and the changes in concentration of electroactive species in solution. Moving into electrochemical non-equilibrium, we have the Faraday law. This law quantifies the relationship between the amount of substance produced at the electrode surface and the quantity of electricity passed through the system. Another important equation is Butler-Worm equation, which describes the kinetics of electron reaction and allowing us to analyze the rate constant. We have the Tafel equation, which is a simplified form of Butler-Worm equation under high overpotentials. Here I'm going to talk about linear sweep voltammetry and cyclovoltammetry techniques. As illustrated in this figure, voltammetric measurements typically requires at 3 electrodes and potentiostatic function. In linear sweep voltammetry, the potential sweeps from initial value to second value over the time and a fixed scan rate, monitoring the resulting current. And the response is then plotted, current versus potential, called as linear sweep voltammograms. While in cyclic voltammetry, a triangle waveform is applied and sweeping the potential from initial value to second value and reversing the direction back to initial value with the results present as current versus potential called as cyclic voltammograms. And here I'm going to talk about electrochemical sensor. So electrochemical sensor is a device which generates electrochemical signal based on electrochemical reaction occurs between the receptor and the transducer and the analysis on the transducer surface, and it categorizes by its measurement principle into potentiometric, amperometric, and voltammetric. From these letters, several voltammetric techniques that are used in electrochemical sensing, which such as linear voltammetry, cyclic voltammetry, and difference fields voltammetry and square wave voltammetry. In other hand, in the development of electrochemical reaction for its performance, different specific characteristics in defining the performance of electrochemical reaction are sensitivity, selectivity, limit of detection, linearity, and reproducibility. And electrode materials have playing a pivotal role in performing the performance of electrochemical reaction, among them carbon-based electrodes, which they are commonly used for several electrochemical applications, such as environmental monitoring, medical diagnostics, food safety, and industrial process control. Now moving to describe briefly the experimental and simulation methods. All electrochemical experiments were performed in single compartment cell using screen-printed electrodes, which contains graphite working electrode, contour electrode, and the reference electrode. The experimental studies were conducted. For the first study, a potassium ferrocyanide in the presence of potassium chloride was tested under the specific conditions. For the second study, a dopamine solution was also tested in phosphate buffer solution under the specific conditions. For the third study, uric acid solution was tested also in phosphate buffer solution under the condition as dopamine. And for the third study, ascorbic acid solution and phosphate buffer solution was tested under the same conditions as dopamine and uric acid. With the aim to determine the electrochemical properties of electrochemical system via the use of linear voltammograms, we have used the following methods. Firstly, a Tafel plot was used for the calculation of charge transfer coefficient. Second, a semi-integral method used for the determination of diffusion coefficient. To simulate linear voltammetry for soluble systems, the case steps in defining the system are as follows. To simulate linear voltammetry, we have used the semi-analytical simulation, and the clearly strategy for this method is presented in this figure. Now moving to how to simulate linear voltammetry for soluble systems. To simulate linear voltammetry with soluble systems, the case steps are as follows. Considering an electron transfer reaction involving soluble species, the system was considered to be quasi-reversible, and the electrokinetics is governed by the Bittler-Volmer relationship. The electrode potential is linear via the use of linear sweep voltammetry, and assuming that the equilibrium is achieved at the electrode surface, so the Nernst equation was used. The movement of electroactive species to electrode surface is governed by the diffusion mode using the second Fick's laws with assuming initially and boundary conditions. Before the computation of current potential expression, it is necessary to know the concentration at the electrode surface of redox and oxide species as function of time. Here, a partial differential equation was produced, which needs to be solved. Using semi-analytical simulation, the solution procedures is divided into basic parts. In the first part, analytical solution is applied by using Laplace transform and inverse Laplace transform to solve the partial difference equation. To solve the partial difference equation into integral current time equation. This part is followed by converting the dimensional parameters into the dimensionless forms. In the second part, numerical solution is applied using integral subdivision and integral by parts, leading to a current potential expression that enable to predict voltammetric responses. After the numerical resolution and obtaining the current potential expression, we implemented the developed algorithm for LCV for soluble system in Fortran, and we analyzed the data. And by analyzing the data, we are able to predict current potential voltammogram. Now moving to the main section is results and discussion, starting with theoretical results. Here we have presented a qualitative and quantitative analysis of linear sweep voltammetry for soluble system. First, we examine the effect of kinetic rate on linear sweep voltammograms for a specific value of charge transfer quotient equal to 0.5 as presented in this figure. Before this, I would like to remind that the dimensional rate constant was expressed by lambda and was expressed by the following equation. And from this figure, and by full analyzing of voltammetric peaks of these curves, we have evaluated the dimensional peak currents as function of dimensional rate constant, and the results are presented in the following table. When we look at this table, the data show that three kinetic regions can be distinguished. For the kinetic rate is greater than or equal to 10 power 3, the dimensional peak currents remains constant at the value of 0.4463. This value is reported previously for irreversible system. For kinetic rate is less than or equal to 10 power minus 3, the dimensionless peak current keeps constant at the value of 0.3505. This value is reported previously for irreversible system. And for kinetic rate between 10 power minus 3 and 10 power 3, the dimensionless peak currents are closely dependent on the dimensional rate constant, and this result is corresponding to quasi-reversible system. Second, we have analyzed the effect of charge transfer coefficient on a series of voltammograms calculated at different value of standard rate constant, and alpha was varied from 0.2 to 0.7, which indicating that for kinetic rate equal to 10 power 3, there is no effect on voltammograms, and this result is agreeing with the previous results for reversible system. For kinetic rate equal 1 and kinetic rate equal 10 power minus 3, as alpha increases, there is a slowly increase of the peak current and the peak potential. For kinetic rate equal 10 power minus 3, both peak current and peak potential are closely dependent on the charge transfer coefficient. As alpha increases, the peak current increases with shifting the potential toward the positive values, and the curves are totally separated. This finding is corresponding to irreversible system. After that, we have investigated the coupling effect of both parameters, dimensional rate constant and charge transfer coefficient, linear sweep voltammetry responses, in which different kinetic diagrams were represented and a series of equations were developed. In the first diagram, which presented the peak current as function of both parameters, the dimensional rate constant and charge transfer coefficient, finding that this diagram exhibits sigmoidal forms, and the data was perfectly fitted by a Boltzmann function, giving the following equation. From this diagram, a linear linear relationship. We have extracted a linear relationship. A specific range describe the relationship between the peak current and the above parameters, dimensionless kinetic rate and charge transfer coefficient as presented in this figure. And the data was perfectly fitted by a linear function giving the following equation. In the second diagram, which presents the variation of the half peak width as function of the dimension rate constant and charge transfer coefficient, it has also a sigmoidal dependency, and the data was perfectly fitted by a Boltzmann function. We have obtained the following equation. Furthermore, a linear relationship was also extracted in specific range and was also perfectly fitted by a linear function giving the following equation. These fitted equations enable quantification of the electrokinetics from simple peak current, peak potential, and half peak width measurements of the experimental linear voltammograms of either reversible, quasi-reversible, or totally irreversible electron transfer process, while the value of Alia is known. While in the third diagram, which presents the variation of the peak potential as function of the above parameters, finding that this diagram exhibits a quadratic shape and different linear parts were extracted in specific ranges and were perfectly fitted by linear function giving the following equations. Moving now to the second section of results and discussion is theory experiment validation. This section includes two parts, starting with electrochemical oxidation of ferrocyanide. As presented in this figure, we have investigated linear voltammetry experiments related to the electro-oxidation of ferrocyanide recorded at different values of scan rate ranging from 30 millivolts per second to 200 microvolts per second. As we have observed that as the scan rate increases, the peak current increases, with shifting the potential toward the more positive values, indicating that the charge transfer is not reversible. With the aim to determine the electrochemical properties of ferrocyanide oxidation, we have used the following math. Firstly, a TFL plots obtained from the experimental linear voltammograms of ferrocyanide recorded a scan rate equal to 50 millivolts per second is present in this figure, and we have obtained that the charge transfer coefficient of ferrocyanide oxidation equal to 0.259. Second, to determine the diffusion coefficient of ferrocyanide oxidation, we have used the semi-integral method, which presents this figure that the semi-integral plots as function. The semi-integral plots obtained from the experimental linear voltammograms of ferrocyanide oxidation recorded at 50 millivolts per second, and we have found that the diffusion coefficient of ferrocyanide oxidation is equal to 6.45 times 10 power minus 6 square centimeter per second. To determine the standard rate constant of ferrocyanide oxidation, we have used the developed equation as seen in this section of theoretical results, and the results are shown in the following table. Then, to validate the applicability of the developed equation, a simulation procedure was used, and we have simulated the theoretical voltammograms using the obtained values of charge transfer coefficient and diffusion coefficient and standard rate constant that presents in previous slides, and compared it to experimental voltammograms of ferrocyanide oxidation recorded at a scan rate of 50 millivolts per second, as presented in this figure. We have observed that the voltammograms obtained from the values of standard rate constant using the developed equation have a good agreement to experimental voltammograms and are very closely, and especially obtained with equation 1 and equation 3 and equation 5, which corresponded to peak current and peak potential. Moving now to the second validation, electrochemical detection of dopamine, uric acid, and ascorbic acid. In analysis using a cyclovoltammeter for electrochemical detection for dopamine, uric acid, and ascorbic acid, first we examine the effect of scan rate on the oxidation of the three molecules as indicated at the top figures. The results show as the scan rate increases, the peak current increases with shifting the potential toward the most positive values, indicating that the charge transfer coefficient is the charge transfer kinetic is not reversible. In the bottom figure, which presents the variation of the anodic peak current as function of square root of scan rate, indicating that a linear relationship between the anodic peak currents and the square root of scan rate, indicating that the oxidation of dopamine, uric acid, and ascorbic acid is diffusion controlled process. Second, we investigate the effect of concentration of the three molecules as presented in the top figures. The results show that the anodic peak currents for dopamine, uric acid, and ascorbic acid increases with increasing their concentration. The corresponding plots which present the variation of the anodic peak currents as function of their concentration indicate that a linear relationship. Specifically for dopamine, the linear range is 1 to 500 micromolar, with a limit of detection is equal to 0.89 micromolar. For uric acid, the linear range is 1 to 200 micromolar, with a limit detection limit of 3.2 micromolar. For ascorbic acid, the linear range is 5 to 500 micromolar, with a limit detection limit of 9.19 micromolar. In this table, we compare the obtained results for determination of dopamine, uric acid, and ascorbic acid using screen-printed electrodes. A comparison suggesting that the use of any modified screen-printed electrodes demonstrate a good performance in detecting dopamine, uric acid, and ascorbic acid. Now, with the aim to determine the electrochemical detection of electrochemical properties of the oxidation of dopamine, uric acid, and ascorbic acid, we determine the charge transfer coefficient using TOEFL plots. In this figure, which presents the variation, the TOEFL plots obtained from linear sweep voltammograms of the oxidation of dopamine, uric acid, and ascorbic acid at scan rate of 100 microvolts per second on screen-printed electrodes. And for calculation of the fusion coefficient of dopamine, uric acid, and ascorbic acid, a semi-integral plot obtained from the experimental of linear voltammograms of dopamine, uric acid, and ascorbic acid was presented in the bottom figure. And the obtained results of the charge transfer coefficient and diffusion coefficient of dopamine, uric acid, and ascorbic acid are presented in this figure. Moving now to determine the standard rate constant of dopamine, uric acid, and ascorbic acid oxidation, we used our developed equations, and the results are presented in this figure, which noted that the values of standard rate constant for dopamine are higher than those obtained for uric acid and ascorbic acid. To validate the applicability of the developed equation, we have simulated a theoretical voltammograms obtained using the obtained value of charge transfer coefficient and diffusion coefficient and the standard rate constant as presented in the previous slides, and compared it to experimental voltammograms for dopamine, uric acid, and ascorbic acid oxidation recorded at scan rate of 100 microvolts per second as presented for dopamine. The simulation results showed a good agreement between the simulated voltammograms and experimental voltammograms, especially those obtained by equation 1 and equation 3 and equation 6. For uric acid oxidation, the simulation voltammograms are good agreement with the experimental voltammograms, especially those obtained with equation 1 and 3 and 5 and 6 compared to equation 2 and 4. In the case of ascorbic acid oxidation, firstly, a calculation was performed using a number of electrons equal 1, and the results show a good agreement between the simulated voltammograms and experimental voltammograms, especially those obtained with equation 1 and 3 and 5 and 6, compared to equation 2 and 4. Now moving to conclusion and perspective works. This study has made a significant contribution to the development of the theory of linear voltammetry for electrochemical soluble redox couples. The simulation of linear voltammetry was based on the diffusion mass transfer and the Bittler-Werner kinetics using a semi-analytical method. In the simulation study, theoretical analysis of linear voltammetry responses was presented through the coupling effects of both alpha and lambda on peaks characteristics, including peak current, half peak width, and peak potential. Different kinetics diagrams were established. Based on the qualitative and quantitative analysis of kinetics diagrams, limitation zones for reversible, quasi-reversible, and irreversible systems were obtained. The reversible zones is situated in the range of kinetic rate is greater than or equal to 10 power 3. The quasi-reversible zone is situated in the range between 10 power minus 3 and 10 power 3, and the irreversible zone is situated in the range of kinetic rate is less than or equal to 10 power minus 3. A series of kinetic equations were developed which enables an easy determination standard rate constant for quasi-reversible soluble systems. To verify the obtained theoretical results, the electrochemical oxidation ferrocyanide on screen printed graphite electrodes was studied. The different kinetics properties of the oxidation ferrocyanide were determined using different approaches. Using the developed equations, the standard kinetic rate constant was determined, revealing that the electrochemical oxidation ferrocyanide on screen printed graphite electrodes is a quasi-reversible process. In the application of electrochemical sensors, voltammetric analysis presented a good performance on screen-printed electrodes for dopamine, uric acid, and ascorbic acid detection. The kinetic and mass transfer parameters of the detection of dopamine, uric acid, and ascorbic acid on screen-printed graphite electrodes were obtained using approaches presented in this thesis. The electrooxidation behaviors of dopamine, uric acid, and ascorbic acid were identically quasi-reversible processes. The results obtained made it possible to establish diagnostic criteria allowing the calculation of the kinetic parameters of quasi-reversible soluble systems. As perspective works, proposing an extension of our approach to analyze cyclic voltammetry responses more comprehensively, suggesting to investigate the impact of combined anodic and cathodic transform coefficients on refining the theoretical equations developed. I have published my article in the Journal of Electrochemical Acta. Also, I have participated in various international communication and national communication. And with that, I would like to thank my supervisor for constant support and guidance throughout my study period. And also, I'm thankful to co-supervisor for your support and advices. I would like to thank the thesis committee for your time in contributing to this work. Also, I would like my family for your continuous encouragement and support throughout my years of study. And thank you for attention. Any questions or discussion part are welcome.